Do I have? Okay. Do I have? Well, okay. Hi. So since there's no chair today, I'm going to introduce myself, I guess. So I'm Johanna Devaney. There's a little bit of. Can we adjust something? Okay. Can you hear me still? Okay. So I'm going to be talking to you today about a toolkit which I've been working on for several years now, which is for analyzing recorded musical performance for which a score is available. Okay, let me just. Okay, how's that?
Just push it a bit up.
Okay. There we go. Is that better? Okay. Okay. And everything sound okay in the audience? Okay. So because I feel like there's still a tiny bit of an echo. Okay. So because this is a demonstration / workshop, not quite clear on what the distinction is, I'm going to open the floor for questions as we go. So if anything isn't clear, please let me know, and then that way it will hopefully help you understand what I'm talking about subsequently. But if you have any kind of like big picture kind of questions or comments, then we'll leave that for the question period at the end. So we'll go for about 45 minutes, and then there'll be a question period. Now, at the moment, this is all in MATLAB. One of the goals of my project is to kind of move it into Python. But if you are a MATLAB user and you're interested in following along, you can either download individual zip files from Moodle, or you can follow this tiny URL, which has everything inside a single zip file, and then you can open it up and it'll give you all the code that I'm going to be talking about at various points during this presentation. But to begin with, I'm going to give you an introduction and then a brief history about quantitative approaches to music performance analysis to orient this work a little bit within the psychological tradition, and then get into the details about my tools for extracting performance data before giving you some ideas about the future directions for this work. So the first question is, why do we want to study musical performance? Now, thankfully, at this conference, there's been enough people working on performance and giving presentations that, generally this is something which seems to be fairly well acknowledged. But to kind of give an overview, essentially the performances convey musicians' interpretations. And so it's useful to be able to have some measurement of the performances in order to understand those and to examine those in detail. Also, the performances are what the listeners actually hear. So if you're interested in reception, it's useful to be able to study the performances in detail in order to make that connection. Also, studying performance can help us gain insight into the available range for extended techniques on instruments, how individual performance practices evolve as they gain more experiences, and then more broadly, how performance practices evolve over time. And also, observing performance practices and how they relate to musical materials can help us develop models of expressive performance. So to be very specific about what I'm talking about today, when I talk about analyzing musical performances, I'm speaking about recorded musical performances, because specifically I'm looking at performances for which a musical score is available, because this has allowed me to solve some of the signal processing issues. And that means that I'm also taking advantage of the fact that I'm doing this not in real time. And so the recordings have to be recorded, or the performances have to be recorded. And then what I've been working on, and this is something that may be, in the future something I change, but at the moment is measuring performance parameters at the note level, and specifically timing, dynamics, tuning, and timbre. And so the challenges in doing this are first accurately extracting low-level data, especially when more than one instrument is playing. And so this is the location of the notes, and then information about the frequency and the power of each of those instruments. And then the next challenge is modeling the low-level data in perceptually meaningful higher-level parameters. So you would have, say, a number of estimates over the duration of the note for fundamental frequency. How do you model that as a perceived pitch estimate for the duration of the note? And then the next thing is to encode these parameters in a shareable way that is appropriately linked with other musical information. And so most obviously you can link this back to the score, but also, and I'll talk about this towards the end of the talk, if you have some information about what the performer was intending to do at that particular point in the piece, that you can actually encode that information in a way that is directly linked to the data that you've extracted. And this allows you not only in your own research to actually come back to this and do more studies, but also because, although I'm calling this the Automatic Music Performance Analysis and Comparison Toolkit, it is not fully automatic yet. There is a certain amount of work which is being undertaken by the researcher. And so if you're able to actually share your data in a commonly readable format with other researchers, this expands the amount of research that people can do generally on music performance analysis. So what I'll be talking about today is this MATLAB-based toolkit. And the basic idea, and here this is dealing with a monophonic case, is that you have the musical score, which is encoded as MIDI. If it's vocals, you may have lyric information. And then you have the audio, and you align these to find the locations of the notes. And from there, you're able to do analysis, which will give you note-level descriptions about all of the notes. And you'll notice as I go through this that all of the examples I'm giving and a lot of the assumptions that have gone into this code at present are based on singing. And this is twofold. First is that my research is predominantly on singing. And second, that because singing provides some particular challenges given the flexibility of the voice, my theory has been that if I can solve this for singing, then dealing with other instruments should be more straightforward. One of the challenges I have going forward, and one of the things where I'm like doing workshops like this and trying to get people, interested in these tools, is if people are actually working on other instruments and interested in using these tools and have examples of recordings from these instruments, that gives me the opportunity to work with people to actually expand it to work for other instruments. So that's my first pitch, and I'll come back to my pitches later on. But let's get back to the kind of more general overview and specifically the brief history of quantitative studies. So really this goes back to the birth of recorded media. So, as soon as people were able to actually record sound, people became interested in analyzing it. But the biggest kind of large-scale study of musical performance took place in, took place in, okay, this is actually frozen. That's why that's happening. Took place in Carl Seashaw's lab at the University of Iowa in the 1920s through 1940s. And they studied dynamics, timing, intonation, and vibrato in pianists, violinists, and singers. And when you look back at the work, it's like, by modern standards, they did a modest amount of musical examples. But when you look at the equipment that they were using, it's actually staggering that they analyzed as much as they did. So they made use of piano rolls in some cases for piano performances in order to get timing and loudness information. They studied films of the movement of piano hammers during the performance. And then for the violin and for the voice, they made use of phonophotographic apparati. And here is a picture of Seashaw literally counting the number of cycles per second in a time-domain representation of the waveform. So this was an insane amount of work. I've actually spent some time digitizing the representations that have been published in Seashaw's manuscript. And one of the nice things is they were quite systematic in that. So they actually mapped everything out with respect to time and with respect to a vertical scale for pitch and loudness. And so, we can kind of recover some of that and look at it comparatively. But ultimately, it isn't that much because this was incredibly difficult work. And perhaps because of the complexity of this, sort of interest sort of waned a little bit. So we have some small spikes in interest kind of in the next 40 years. One of the most notable was Charles Seeger, who was an ethnomusicologist who was interested in doing automatic transcription and developed this tool called the mellograph. which didn't really develop much of a following because around the same time, ethnomusicology took more of an anthropological turn and sort of moved away from these issues of transcription. So it's actually in the 1980s where you had the disc clavier and then MIDI technology develop that you start to see a resurgence of these types of research questions, and specifically focused around the piano. And the reason why the piano was so appealing was, first, there was a large amount of solo repertoire. So if you want to have your performer come in and perform in a way that is familiar to them, that is ecologically valid, the piano is a great instrument because they spend a lot of time doing this. Also, because of the instrument's percussive nature, it's less ambiguous as to where the onset is actually happening. And then because there was the feasibility of using the specially equipped pianos, you were able to collect a lot of data when you had people come in and do experiments. Now, the challenge there is that you're only ever studying the performances for people who come in and perform on those instruments. So there was still the question of what do you do if you want to study like Horowitz or something, you know. And so there were some kind of starting in the 90s where computer technology started to ramp up, people started to look again at existing recordings. And so you have people who started looking at intonation, and one of the nice things with intonation is that that's predominantly solo instruments. So the initial way that people were doing this was actually very similar to seashore. But instead of being at some kind of phonophotographic device, they were actually looking at a computer representation of the spectrogram and trying to make assessments about what was happening there. And then people started to develop better estimates for fundamental frequency, and then you were able to actually do that automatically. And then more recently, people have done computational models of piano performance. And this has largely been coming out of having like a disc clavier or a Bosendorf and being able to collect large amounts of data. But it's also led to developments in signal processing algorithms for analyzing existing piano recordings, because you then have this training data that's linked between what the recording actually was doing in terms of the notes and then the recording itself. So overall, this has been a long history, but there's still a lot of work that we can do in terms of being able to like actually just, you know, sit down at the computer and say, here's a recording, what is it that's actually going on with the performer? So in order to address this, I started to develop tools for doing automatic analysis of recordings that were guided by a musical score. And so the history of AMPACT goes back, I guess now 7 years. So first I started by doing monophonic alignment, where I developed some tools for very robustly estimating the location of singing notes based on the having a MIDI score. And then from there I started to extract monophonic pitch and loudness information from that. And then a few years later I dealt with the issue of polyphonic alignment. And the challenge of polyphonic alignment is that at the time, it was fairly standard to be able to take a MIDI score and align it to an audio score, but it treated all of the notated simultaneities, like the chords, as actually happening at the same time, which is never the case. It's never the case with the piano, it's never the case with a group of people playing together. And so I developed some tools for actually finding all of the individual offsets and onsets at each of those transition points, which, as I'll talk about later, is useful both for being able to get that timing information and differentials, but also for guiding the signal processing algorithms. And then within the past year, and really it's kind of like the past 2 years, I guess, at this point, because it's just now it's coming out into AMPACT, but it's been a couple of years' work. Polyphonic pitch, loudness, and timbre estimation, which is guided by the polyphonic alignment, and then also best practices for encoding this data and extensions to MEI and humdrum in order to do that. So if you want, as I mentioned, if you want to work along, I've zipped up all the code together. If you just want to listen, I have the code available on Moodle. I also have the slides available on Moodle. So I'm hoping that there is sufficient detail in these slides that if you decide that you're interested in this and want to check it out later, there's enough detail to kind of like work through it and understand what's going on. So if you do download it, you'll want to unzip it, and then you'll want to add the folders and the subfolders to the MATLAB path. And what you may need to do to get this to work is there are some MEX files for the yin algorithm, which you may need to compile. At this point, I'm talking really to people who are already MATLAB users. I'm not going to get into like details of how to use MATLAB. So if that makes sense to you, I'm just going to leave it there. And specifically, we're going to be working with the example script.m, runpolyalignment.m, and polyphonicdemo.m. And I'm going to be very clear about when we're going to actually get into that. So we're going to go through this historically, because it also kind of makes sense in terms of going from like the simplest thing to the most complex. So we're going to start with monophonic alignment. So this we've sort of looked at already, where we have the score, and then we have the audio, and then we have the alignment. And this gives information about where all of the notes are occurring. And sometimes we'll also have lyric information. So one of the things that AMPACT allows you to do, so in the case of singing, is to actually encode the lyric information so that you're able to say whether or not like the notes just changing under the same vowel, whether it's a voiced or an unvoiced consonant. And I'm just going to play you now this audio example. Oh, yeah. So looking at example script, so you have to specify the audio file, the MIDI file, the number of notes. This I may automate at some point in the future. This is where you actually specify what the, whether it's a rest, whether it's a transient, whether it's steady state. So at the moment, this is fairly gnarly to deal with. But this is basically where you're telling it the lyric information. You can actually run it without specifying that, and it'll do its best to figure out where there actually are transients at the beginning of the notes, or whether it just goes directly into the steady state. And then because this is dealing with an HMM, the next part of the code just deals with loading the appropriate information for the hidden Markov model for modeling the transitions between the states. And then here, this is a thing where it's like very explicitly designed for singing right now. But if anybody is working on, say, violin or cello or guitar or clarinet or something, and you have a fair amount of data that's been annotated, we can very easily generate this, generate whatever these requirements are for a different instrument. So that's something where it's like, if you're interested in doing that, definitely send me an email, which I realized I haven't put my email anywhere on the slides. But luckily, my name is not that common, so you can just Google me. Or j@devaney.ca is my email address, if that's of any use. And then you can, depending on it, like you can get fancy with some of the hidden Markov model parameters, but if you just kind of set this to 0, then it's just going to be as simple as possible. And then there's a function called run alignment, which takes the audio file, the MIDI file, the number of notes, what's been specified here, here, and here, and it returns the state sequence as well as all of the pitch and power, all the frequency and power information. So this is the function that it calls. So as I mentioned, it takes in all of this information, and then what it outputs is the times for all of the states, which then can get converted with the next function into the notes, a spectrogram of the audio file, and then all of the information for which you get from yin, which is an autocorrelation-based algorithm for fundamental frequency and power estimation. And so this is what happens. You can also visualize it. This is what happens when it fails. Because I figured I should be honest about the fact that this works really well sometimes, and then sometimes you get an audio file where we end up with some mistakes, right? So we would expect to actually see this line extending all the way along here, and this line extending here. So this is where I was saying it's not completely automatic. Once you've actually done the calculation, you then run the visualization function, and you can see how well it performs. So if it actually has identified everything properly, you're good. And if not, you go on to the error correction step. And what I recommend for error correction is actually then using Audacity. So you can use this function to get the onset and offset times from the output of the earlier function. And then you can write these in a way that's actually readable by Audacity. And so then going into Audacity, these on the top line are the labels that I messed up. And then these are the ones which I then corrected. So you can see here that it's not saving you all of the time, but at least you only have to do a correction as opposed to having to do a manual annotation from scratch. So it is saving you a little bit of time. And then once you've done this, you can reload it, you save it and you reload it back in, and then you get the timing information from that. So one of the longer term goals that I have for this is to actually move from it being research code into something with a graphical user interface where you would actually do these corrections within the environment, and then these corrections would actually then go back and actually help to improve the underlying algorithm. So once you have this, you can actually generate a new version to actually hear the differences. So this is taking advantage of the MIDI toolkit, the MIDI toolbox from your vascular. And so here we have the information for the original and the information for the adjusted one. And so if we see here, we can see the differences in the duration between the two versions. And I'm going to play them for you with a piano timbre so that you can actually hear those onsets much more clearly. So that was the original. And that was the performance. And we can see this visually between the two representations of how much longer the actual performance was than the original, and the differences, some of the subtle differences in terms of the inter-onset intervals. So that's the monophonic alignment. And then from there, once you have these timing points, you can actually go in and estimate the parameters for each of the notes. And so initially I was just looking at pitch and loudness. And so specifically, the parameters related to pitch and loudness were perceived pitch, which here we have just a simple sine tone. And so just taking the average over the duration of the note is fairly straightforward. What's actually implemented in MATLAB right now is a perceived pitch model by Gockel and Moore, which does a weighted average. But one of the nice things with it being a coding environment is you could use whatever weighting average you want, right? So it's quite flexible. I also calculate vibrato depth and vibrato rate by analyzing the pitch trace with an FFT and then looking for the peaks in the FFT to represent the depth and the rate. And then I also do some calculations for the slope and curvature of the trajectory, and that is done, and I'll show a little bit more information about that in the next slide, by applying the discrete cosine transform to the trace. And what that does is it decomposes the trace into a number of coefficients, and the first couple of those can give you information about the overall increase in slope or curvature for those. And then I also have the Genesis toolbox, which is included, does the calculations for perceived loudness, and there you have the choice between either using the Zwicker or the Moore models, and so that's all very flexible. So this is the code for doing that. So either the function called getSentValues, which gets you the sense values for each note. There's the calculations for getting the pitch and the vibrato data, and so that you just input the cell array of the cent values for each note along with the sampling rate, and then it gives you the estimates for each note for the depth, for the rate, for the interval size, which is the difference in perceived pitch between sequential notes, and then also the perceived pitch for each of those notes. And then for doing the slope and curvature, it's inputting the signal, which is the FO trace, and then the number of coefficients and the sampling rate. And so I've been using what comes back as being in MATLAB, it would be the second and the third coefficient to be the slope and curvature. And then the next thing is just basically a wrapper for the loudness, where it's putting in the audio file and the times, and then it returns minimum short-term loudness in zones versus times, and then a complete structure that comes out of this Genesis toolbox that you can do with whatever you want. So that's kind of like the core of where AMPACT was basically when I finished my dissertation at McGill in 2011. And then subsequently, I was able to get some funding from the National Endowment for the Humanities to kind of start to move it along a little bit. And that's why I started to work on the polyphonic alignment. And so the first thing was this issue of polyphonic score alignment. So if we look at this example here, so if you look at these blocks, you can see like it's saying, okay, all of the notes are starting here, and then the next notes are starting here. But what the existing alignment algorithms at the time weren't capturing was the fact that some notes would end early, some notes would start early. And so you weren't actually getting any detailed information about what was happening at those transition points. You were just getting the idea that basically here the notes are more or less starting or stopping, which is fine if you're doing score following. You know, like if you're in some kind of like real-time environment and you just want to have your computer track where roughly you are in the music, that's great. But if you're interested in looking at the individual timing differences between lines, which can be useful for figuring out, say, an ensemble who might be leading, or whether it's consistent that one person is coming first. There's been a lot of work on the piano to see where the melodic line is, and behavior of how pianists treat the melodic line. This becomes very useful for that. So in order to do that, there is this run poly alignment algorithm, or function, which will actually work as a demo as well. So you can put in an audio file, a MIDI file. Again, because it's using hidden Markov model, you have to have these Mies and covariance values, and then the type or instrument that you want to use for each line. And then it estimates all of the onset times and all of the offset times. But you can also just run it, and it has default values. So if you're interested in just sort of seeing what it outputs, you can run it with the default values just by calling its name. So once I had that, I was able to then use this to guide a signal processing algorithm to actually get information about frequency and power for all of the nodes. And that's the polyphonic parameter estimation, which is the most recently released version. So this is a visualization of what that actually looks like. So here we have a score, and then we have a spectrogram, and we do the alignment. And down here, you can see the estimates for the fundamental frequency. So, and it's also, if you can tell, I don't know how well you can see it, but there's actually segmentations here. So this isn't continuous. This is segmented by note. So we have the note here being represented here. We have the note there being represented here, and so on and so forth. And so the top line is in blue, the second one in green, and then red, and then purple. And those colors also correspond over here for the power estimates for each note, although obviously those are much more overlapping than the separation by pitch. So I'm just going to play this audio for you. And what I'm not visualizing here is not only am I extracting these FO estimates and these power estimates, but for each note I also have estimates of the full spectrum as well. So these FO and power estimates are being calculated by having for each note all of the frequency content and the energy for all of those frequencies as well. And so from that, I'm able to do the calculations for perceived pitch and vibrato, and slope and curvature and perceived loudness. And I've also added in a few additional parameters as well. So with respect for the fact that I'm studying singing all of the time, I've added in parameters like jitter and shimmer. And then I've also added in some timbral information. information as well. Now the timbre information is very classic, like, you know, here's the centroid and the slope and the flatness and the flux. And then the harmonics to noise ratio is a bit hand wavy because obviously it's hard for me to properly estimate the inharmonic partials, but it does something. So I would say that this is definitely the weakest part of the toolkit right now, and something where I'm really interested in like collaborating with people who are working on timbre, so that I may be able to like actually expand this in a way that would be really meaningful for people who are working on these problems. And so to run this, there's the polyphonic demo.m. And so this will take the audio file, the MIDI file, again, these means and covariances and the voice type, and it will run the polyphonic alignment function that we just saw a few slides ago. And then for each note, it will go through and it will estimate the FO information. And then from there, it'll also estimate all of the perceptual parameters. And so what that ends up looking like would be for a single note, there would be a perceived pitch estimate, a jitter estimate, vibrato, rate and depth, shimmer. And then there's also these trajectories that you can get, because one of the things that I think is really important is that you're not just always getting out these like single values and you just have to depend on whatever somebody else has implemented in order to have a note-wise descriptor. That it's really important that you actually can get out the frame-wise lower level data, because you may want to do something completely different than what I've actually decided I want to do for my research. Yeah. Probably like oh, okay. Oh. I can say, okay. So there's a, You okay? Oh, I'm here. Yeah, I don't have to lean over there. Okay. So the question is there a minimum pitch separation that needs to be used here? At least a tone, just because of the window that's around it. But for most tonal music, it's not much of an issue. Yeah. Yeah. Yeah, a whole tone. Yeah. And so likewise, you know, I have this like mean spectral slope, but I'm also outputting all of the frame-wise values, because that might not be what you're interested in. Can you hear me okay? Oh, okay. Yeah. Yeah. Yeah.
For polyphonic data, does the algorithm also do source separations, or do you need separate recordings?
No, it's doing source separations from the score.
Okay.
Yeah. So basically what it's doing is it's doing the alignment, and the alignment for each note is identifying a time frequency region that then I can look at in order to calculate frequency and power information.
Okay. And how does it deal with, because I imagine for timbre, for example, sometimes you can have non-synchronous onsets of harmonics for different instruments. How does it tease those apart as well?
So what it's currently doing is it's just looking over the entire duration. So it's not actually calculating onsets for that. But what the problem is that it's not real. I haven't figured out a really good way to properly capture the inharmonic partials, and that's the next big challenge I have to deal with. But it is getting the entire duration of the note. So if there's some asynchrony in those onsets, it's not identifying where those are, but it's able to get that. Okay. Okay, how's that? Okay. So then the final thing that I wanted to talk about today was the encoding. So one of the things which I realized when I started to look at encoding formats was that, and this is why there are multiple encoding formats, there is no one format which is going to be, you know, solve everything or capture all of the information I want. So it's actually implemented with two different formats. The first is humdrum, and here you have like the standard humdrum encoding, and then there's also like existing humdrum things for like the start and the duration of the note, but then adding in information, like just basically defining, you know, slope and curvature and vibrato depth and whatever, and then the same thing for the loudness, and then the same thing for the timbre information. Now, one of the reasons why I thought it was useful to use humdrum is that it's fairly straightforward if you are interested in actually also having descriptors like, let's say, at the beat level or at the measure level, then encoding that in humdrum is pretty straightforward. And that you can get out of some of, like, you have to hack the toolkit a little bit to get that. But it was something which I thought, when I was actually spending some time thinking more generally and not just in terms of my toolkit, what would be useful things to do when encoding performance data, I was like, okay, sometimes it may be that you're actually just looking at beat level things or something. So I've put out that availability in humdrum for those kind of tasks. But also, I thought it was important to also use the music encoding initiative, because one of the benefits of the music encoding initiative, although it's incredibly verbose and not as readable as humdrum is, which is the other nice example of humdrum, is that you can actually encode so this is for a given note, you can actually encode not just these note-wise summaries, but you can encode a vector of all of those frame-wise estimates. So if you're interested in actually retaining some of that low-level information, it's not possible to do that within humdrum, but you can do that within MEI. So that's why there's these two encoding formats, which I've specified and I'm now in the process of implementing within AMPACT. The other thing that's really useful for MEI is that you can also encode text very easily. So if you had, say, either things that like performance directions that were written in the score, or you had notes from the performer, or even notes to yourself, you can actually encode that directly into the MEI format in a way that's directly linked to specific points, not only in the score, but then also in the audio. And so you can link that all together. So now at the conclusion, so I'm actually moving along quite quickly. So hopefully we have some questions to fill up the rest of the time. So to summarize, these have been the kind of like 5 main stages: the monophonic alignment, extracting information from monophonic audio, and then polyphonic audio as well in these encoding formats. And so moving forward, what I'm really interested in doing is expanding this to work with other instruments, which I've mentioned already. I'm also going to be porting this to Python so that's a bit more accessible. But also in combination with that, developing a web-based graphical user interface, which have these tools that I mentioned for doing manual corrections, and then also adaptive learning on those corrections so that it actually continues to improve the algorithm. But what I'm most interested in kind of coming here is to hear, like, from people who are interested or doing this kind of work already, what are the kind of things that would be useful? Because at this point where I am of moving from like research code into a product, essentially, like an open source community-based product, is really helpful to actually get information about how it might be used. So there is a website, so you can go there and kind of get documentation and a link to like the GitHub site. And so I'd like to now thank you for your attention. And see if there's any questions.
Thank you. This is very interesting. I did not catch, when you do polyphonic, do they have to be recorded at separate channels, or it's a single?
Yeah, single channel.
And does it help if you have them separately?
Yeah, if you have them separately, then you can treat them as monophonic. And so there's less error. And then certainly for things like the timbre questions, where it's not capturing the inharmonic information, you can capture that easily in a monophonic file. It's just when doing the source separation in the polyphonic file, there's no information in the score that's explicitly going to tell you what inharmonicities to assign. So the way to solve that, which I haven't done yet, is that if you have information about what the instruments are, and then you can do some kind of subtraction because you know what all of the harmonic information is, and then given the residue, you try and assign that residue to the current instruments. That's like a future direction for that. But you can get it. It's very straightforward to get that from the monophonic.
Thank you.
This is really impressive stuff. I have so many ideas of things I'd like to play around with. I'm curious, do you have any thoughts about what instrumental timbres do you think would be the most challenging for this to handle moving forward?
So I think like things like guitar, where there is a lot of inharmonicity on the, like anything where you're sort of like attacking a string, like that I think will be challenging. I mean, really, like the voice in and of itself is kind of challenging, but if you're looking at a particular vocal style that is looking for a clear voice, that's less of an issue. But I think anything where the onset is going to be particularly noisy is going to be challenging to capture that information if you want to.
Is it hard to identify the note or just hard to like extract all of it? I can see why it's hard to assign, which pitch the non-harmonic stuff might. But if you're trying to like pull out from a flurry of piano notes or something, and you can figure out, which overtones map onto that, wouldn't you be able to get the onsets and everything, or a lot of information?
I'm just talking. I was still on the train of timbral information.
Got it.
But
that makes sense.
For piano, it's like I'm not actually convinced that this is that useful for piano because people have been doing some fairly impressive work using ways of decomposing the signal into the notes and stuff. That may actually be the better way to go for this than using the score-guided approach. But definitely, like, the shorter the distances are temporally, and also in terms of frequency, the more complicated it becomes. So yeah, piano would be particularly challenging for that, for like late romantic styles, for instance.
Okay, thanks.
Would you like to tell us what your software does that Pratt cannot do, and vice versa? How does it compare to the features of Pratt?
So in terms of the polyphonic stuff that Pratt doesn't deal with particularly well, I also, because Pratt doesn't really take advantage of the fact that when you're dealing with music and you may have a score, that you can actually improve the segmentation even of monophonic music. So that was sort of my main starting point when I was initially looking at what was available. And I was like, okay, I can do this in Pratt, but I'm always going to be treating the song as speech, and it's not actually going to be able to capitalize on the fact that I know what the notes are. And that's where this kind of moves away from what Pratt.
So the score has to be available as a MIDI?
Yeah.
Okay.
Or, I mean, I guess if you have a scan, you could try doing OMR, but yeah, this requires the score to be digitized in some way, and then once it's in a MIDI file, then that's what's actually guiding that separation in the polyphonic.
That's very interesting because I just in the lab where we asked summer student to spend 1 week transferring from a score to MIDI.
Oh, okay.
And then we didn't know which software to use to match to the recording.
Oh, okay.
Maybe as a potential idea for how timbral, like the library of timbral, or even other descriptors could be extended. Could you think? Well, depending on what way you actually, what's the spectral model currently? It's based on harmonics. I mean,
yeah,
I guess that's this spectral representation.
Mm-hmm.
If I wanted to just come up, or if I had some descriptor in mind, I wanted to integrate.
Mm-hmm.
Could it be programmed in a way that you specify that this should be the format, and I could just create my own MATLAB function?
Yeah. So, like, essentially what is being returned at, like, kind of the later part of the code is a spectral representation for each note. And so you could do whatever calculations you want to do on that. Currently, it's using very basic kind of stuff, but you could effectively do anything.
Yeah, so as a future idea, it might be nice to have some explanations of how to integrate that, that it would pick it up automatically and then output data, and then you could even provide that to others, like as part of the library, once you've tested it, perhaps.
Yeah, and then it's also, one of the things is just like, you know, maybe there are other kind of like frequency scalings or something that would be more useful that could be implemented as well.
Great, thank you.
Do we have a question?
Okay, yes, we're going to go to Argentina here. We're just traveling the world. Just 1 second.
Hi, everybody.
Hi.
Thank you, Johanna, for your presentation. Well, do you have any question to make to Johanna? I think we are quite good here.
Hi.
Thank you for saying hi.
Yes, I can hear you now.
Yeah, we have to turn the microphone off while you talk, otherwise there's feedback. Anyways,
Sorry?
we have to turn our microphone off while you talk, or there's a feedback situation. But thank you very much for your attention, and we'll just continue along in this room.
Okay, thank you very much.
Thank you.
Bye, thank you.
You can leave if you.
Hi, that's just really cool. Maybe I missed this, but so do you have access to the spectral information of each individual note when you're teasing it out of a polyphonic recording?
Yeah, well, it's an estimate, right? So what it is estimating is the fundamental and the partials.
Okay.
So it's not actually capturing any of the inharmonic information.
Okay.
But like I was saying, like I have ideas about how to do that, but that's like the next step.
Cool. Thanks.
Okay. So is any other questions? Okay. Thank you again for your attention.
Thank you, Johanna. Thank you, Argentina.
Good night.
Okay, we're going to set up the next presentation, so it'll be in 13 minutes.
Okay. Oh, that's okay.
Thanks very much. It's great to know about this.
Oh, yeah. Yeah, if you're interested in any questions, definitely shoot me an email.
Thanks.
Is this your laptop or the presentation?
That's the presentation.
Are you the next presenter?
Not the next, but the one after that.
Okay.
So I was just going to load up quick.
Drop on the desktop in a familiar place. I think it's the other side. It's very old.
Can I get you to
Yes. If you can just kind of wag your... That's you?
Thank you for the support.
No problem. We'll try it.
It appears to be here, and it appears to be opening, so that's great.
Great. Do you have...
Audio?
Yeah, it should... Oh, yeah, maybe just check that really quickly.
All right. Might as well.
Yeah, it's worth it. Good
Yep.
enough. Good enough. So, sir, are you doing a thing?
I'm the chair.
Oh, excellent! There's a chair. Finally, there's a chair. I've been the chair all day.
I've noticed.
Should not be the chair.
We have a very nice chair voice.
I have a radio voice. It's the one thing that's working for me.
We have a question from the reply.
It's the one part I like. Are you also presenting, or are you just chairing?
No, I'm the chair. We're co-chairs of this.
Oh, you have two chairs.
Yeah. So when it rains, it pours.
Are you also a chair, Elizabeth?
Yes, and
Okay.
done.
And you're presenting. Okay.
So she's the
what you
first
need.
presenter.
Do you guys know the name of the lady who was just here by chance?
Haley Cragness.
Yes.
This is Haley. She put that Cragness folder at this time.
Hey, Haley. Haley Cragness.
he walked out.
No matter. I'll hang on to that.
Okay.
So you just pop it in on the left.
So, how about I'll announce you, because that would be weird. You announce you.
Do you want to announce us both first and then announce me?
Yeah, I'll do a little intro. I'll announce you. You're probably going to be going to sit down, so how about you deal with that one?
Okay.
Yeah, G-Tool. You guys, have you seen G-Tool?
G-Tool, I haven't seen G-Tool.
Okay. Well, go ahead and load these.
Okay.
Do you guys want chairs up here?
No, so I'm going to sit there. Yeah.
Okay.
So,
Usually, like, I pass you the microphone and you give like a 1 or 2 minute presentation of like what's going to happen and what's the topic generally, and then you pass it to the first presenter. Yeah, that would be great if you're up for that. Yeah. Cool.
how do I know when they have a break?
So what we do, well, I text them, ask them, do you have a question? Do you have a question? Get a response. So
Okay.
try to just take a shot. So like we try and do 2 questions in this room, and then we try and pass it to Argentina for a question or 2. Okay. And then we kind of just keep going here until we're out of time.
So it's live for Argentina, but it's recorded in progress.
Yes. Okay. They might even be watching the city live 14 hours. No, they won't. So yeah, okay, it's just are you doing 20 minutes presentation?
I believe
Yeah. Okay. You want to do slightly longer? It's fine. Oh.
Hey, Elizabeth, how long? You're probably like 12 minute talks.
No, you have
Father time.
Oh, yeah. Get you to load up your.
Oh yeah, I'm all set.
Oh,
yeah,
you're very nice. That's why.
Yeah, with
You presented yesterday, right?
Yeah.
Yeah.
So
Okay.
yes.
Excellent. Excellent. Good. Good to see you again.
Do you need anything from me?
No,